Hello guys, welcome to a new video. Today we're going to be talking about SN2 reactions. So what is the difference between SN2 and SN1 reactions? We're going to be going to over a quick example of an SN2 reaction at the end of the video. But before that, let's see the characteristics. No carbocations. If you saw my video about SN1 reactions, you know what a carbocation is. If not, please go check it out. I put a lot of effort into it. So yeah, go ahead. So remember, carbocation kind of look like this, and it's the step in between. But there is no carbocations for this reaction, right? Because this reaction is a one-step reaction. So things happen like that, right? So a one-step reaction, aprotic solvents. So what are aprotic solvents? So aprotic solvents are solvents that don't have a hydrogen to donate or a proton. Just to recap, aprotic solvents are solvents that cannot donate a hydrogen. We talked about hydrogen bonds the other day. Is only failures, right? So it's oxygen, nitrogen, and fluorine. And aprotic solvents is something that is a bond between a hydrogen and an oxygen, a hydrogen and a nitrogen, right? So as long as those bonds aren't present, that's an aprotic solvent. They cannot donate a proton. It's aprotic, lacking of it. So home examples of aprotic solvents are acetone, ethyl acetate, acetonitrile. You see the trend, like starts with A, aprotic. You can also see there is no hydrogen bonds, right? Or they have like acetone or acetate. So if nitrile groups are also part of the SN2 reactions, they are aprotic, right? So let's get rid of them. Another tip, it's not always the scenario, but it is pretty common scenario, abbreviations. This is not how you spell abbreviation. Okay, abbreviations. Abbreviations, guys, my bad. Abbreviations are aprotic. So DMSFO, DMF, THF, those are aprotic solvents. And those are not always the case. If it has a oxygen and a hydrogen, that solvent will be protic. Sometimes the only other abbreviations have alcohol groups that are oxygen and hydrogen. But most of them, they will have DMS, DMSFO, THF, aprotic solvents. Aprotic abbreviations, A-acetate is lacking of a proton. How you like that, guys? Oh, I'm sorry, guys. There you go. Okay. So, what about the rate? What's the rate constant dependent on? So, we had talked about earlier about in SN1 reactions is only dependent on the substrate. The substrate is what's holding the leaving group, right? In nucleophiles, in SN2 reactions, depending on the substrate and the nucleophile. So this reaction will be dependent on the substrate and the nucleophile. Okay, the geometry. Which geometry is beneficial for SN2 reaction? Pause the video and answer me right now. That was so bad. Okay. SN2, SN1. So we remember for SN1, this is cool because we want to make carbocation intermediates and we want them to be stable. For SN2, this is cool. It's what we want for SN2. It's what we want for SN1 because of the bulky groups. They're gonna do a back attack, so we want a space for them to do the back attack. Something else that happens in SN2, a stereochemistry change. So let's say this, no, SN2. This is now This is a dash. Let's say a SN2 reaction goes this will change backwards. Now, wherever was a dash, it's a wedge. Wherever was a wedge, is a dash. Wherever it's a dash, it's a wedge. SN2 characteristic is that it requires a good nucleophile. Because remember, the living group leaves and it gets replaced for the nucleophile. So it requires a great nucleophile to attach where the living group left. So all nucleophiles are anions, right? Anions means it's negatively charged. Why? We stand from the worst to the best. So the worst nucleophiles to the best nucleophiles. So the worst nucleophiles, it will be water, because we remember the water can act as an acid as a base. So remember, like, nucleophiles are mostly bases. So water is not the greatest. That's not the greatest. So we go all the way here. These are the best nucleophiles. So R represents carbon chains. What else? R represents carbon chains, and Xs represents halogens. Halogens, but fluorine. Halogens is the little row in the periodic table where fluorine is. It's fluorine, chlorine, bromine, iodine, and all of them are good nucleophiles by itself. Like I'm talking about, like diatomic atoms, but not fluorine. So no, I'm talking about atomic atoms. I'm talking about the atom by itself. An atomic atom will be this. Well, it will be this. Well, I was talking about use. Why I keep writing fluorine? Talking about use this, because this will stabilize its own charge. So the smaller the halogen, the better. So fluorine is smaller than iodine. So chlorine is a better nucleophile than iodine. Hello guys, SN2 reactions do not form cations, right? So we have this reaction right now that was on my test, and we want to predict the product. In my test, I got this question wrong because honestly, I didn't know went over SN1 and SN2 reactions, but now we're studying them, right? So this one, this is an oxygen over here, that's what it's telling us, and so it's bound to carbon, and the carbon structure is not gonna change, right? The only thing that's gonna change is gonna be the stereochemistry and the product. So we know that the living group is gonna leave. Living group leaves. So living group groups. So that's gonna be one of our products. The living group leaving, right? And we know that Na is a metal, and we know the metals are positively charged. So that's gonna be the partial charge, and we know this one, sulfur, is gonna be negatively charged, right? So we know this is about to be like that, you know, like those molecules are gonna break like that. So we know this is an substitution nucleophilic attack. Why? Because the nucleophile is attacking. We know this is a SN2 nucleophilic substitution reaction, not nucleophilic attack. SN2 nucleophilic substitution, right? So the nucleophile is gonna get substituted, right? Meaning what? This is nucleophile. Nucleophile. The halogen here is gonna get substituted for the chlorine. Right now we're not putting stereochemistry, but remember that you always have the stereochemistry. So if it's breaking from the S, we want to put the bond coming from the S, because that's the element it's going to bind. The CH3 is going to bind. No, it's going to be the S and the hydrogen. But we're missing one step. What's the step that we're missing? We are missing the stereochemistry changes. Don't forget, SN2, stereochemistry changes. SN1, we have the racemication. SN2, the stereochemistry changes. So what's happening? The hydrogen that was like this, it's like this now. The hydrogen and the other group, the stereochemistry change. So we have the chlorine and we have the spectator iron plus NaO plus. So this is all for SN2 reactions. If you have any questions, let me know down in the comments. Oh,